Hey there, welcome to How to Maths. My name is Mark, and today we're going to be going through some vector calculus, in particular projectile motion, but we're going to build our way up to it by first looking at differentiation of vectors. We're going to look at integration of vectors. We're going to look at vertical motion of vectors, and then finally finish off with projectile motion. If you're here for the projectile motion, make sure you watch the rest because it's going to contextualize what we're doing, and make sure you stick around for the end because we have an exam style question and you don't want to miss that. All right, let's dive into it. Okay, first things first, we have a vector calculus overview. When we derive vectors, we want to derive each of the components individually, and also we want to know that the first derivative of position is velocity and the second derivative is acceleration. Then we also want to know when we're integrating that we must use our constants of integration, and lastly, we can use initial conditions to find those constants of integration. I'm not going to really focus too much on teaching the integration and differentiation techniques in this video. I'm going to more talk about the vector components in particular. Okay, so here we have a vector that we want to find the velocity of, the first derivative being velocity here, and the second derivative with two dots being acceleration. I'm just going to write that to the side here. R of t is the position vector. R dot of t is the velocity. And R double dot of t is the acceleration. So the first one is just going to be 20 in the I direction, and the second one is going to be 15 minus 10t in the J direction. When we find the velocity, the acceleration now, it's going to be nothing in the I direction because it's just a constant, and in the J direction, it's just going to be negative 10j, which actually makes a lot of sense if we think about it, because negative 10 is a good approximation for gravity's acceleration, and the J direction tells us that it's vertical, and the negative tells us that it is down. So this is a good representation for gravity. Nice. Let's go to integration. Okay, continuing on with some integration now. I'm being given an acceleration vector, and now I'm finding the velocity and position from it. Again, I'm going to go quickly through the integration. If you need help with some of these integrals or you don't understand them, either click on the link below where I go through integration in one of my other videos, or leave a comment in the description. I'm happy to get back to you. So I'm going to write the velocity, the acceleration vector, just so I have it as a reference point, minus 12k. And then I'm going to find r dot of t. Integrating with respect to time, it's going to be 10t in the I direction minus 12t in the k direction, plus my constant of integration, number 1. I know there's going to be more because I'm finding position in part B, so I'm just going to use C1, C2, C3. As many constants of integration as you need. I prefer that to using C, then D, then E, then F, and so on, because it can just get confusing with all the different variables. So I like to use C no matter what for constant of integration. Right now I need to find out what the constant of integration is by using my initial condition, which is here. 30i minus 20j plus 10k is the initial velocity. So initially, all of this, the 10ti and the 12tk, are going to be 0 because of the t's turned to 0. So I just get C1, and that's going to equal my initial velocity. So when I sub that back in, we're going to find the velocity of the entire particle. I'm going to collect all my i's and collect all my j's and collect all my k's separately. So in terms of i's, I have 10t in the I direction there, and I have 30i in the 30 in the I direction there, and hence in total I have 10t plus 30 in the I direction. Now my j's, I only have negative 20 in the j direction, so I'm just going to write negative 20j. And in the k direction, I have minus 12t up here and plus 10k over here. So in total, I have plus negative 12t plus 10 in the k direction. Nice. Let's move on to the position vector in part B. Rightio, so B is going to be a very similar process to A. I'm going to write down the position vector is going to be everything else integrated. So I'm going to get 5t squared. Just as a quick reminder, this is going to become t squared on 2, and 10 on 2 is 5. So that's how I'm getting 5t squared plus 30t, and that's all in the I direction. Then I get minus 20t in the j direction, and lastly minus 6t squared plus 10t in the k direction, and my second constant of integration. Now my position here, my initial position is simply 2k. So again, I'm gonna actually not again, this time I'm gonna go through much faster and just look and see that all of my I components have t in them. So when I substitute the initial position, aka when t is 0, all of those are gonna go to 0. So I is gonna be nothing, j is gonna be nothing, and k is gonna be nothing. And therefore I can say as r of 0 equals 2k, this implies that C2 equals 2k itself. Now, if C2 just equals 2k, I'm just going to take the 2 and put it back in these brackets, right? So this C2 being 2k is just going to jump into here. So to save myself a bit of time, I'm going to grab all this, duplicate it, and say r of t equals all this, except we have an extra 2 in the k direction. Nice, we've finished. We've got our position and velocity vectors from an acceleration vector. All right, we've made our way to vertical motion now. So we actually have a worded problem and we've got to infer some information. The nice bit about this question is because it's just vertical, it's just going to be a j component the entire time. So let's dive on into this. If you want a moment to read it, pause the video, read the question, and then let's move on. Okay, so an expression for the velocity of this particle, given that the acceleration is equal to negative 9.8 in the j direction. Therefore, the velocity is going to be negative 9.8 t in the j direction plus constant of integration number 1. And it tells us that that initial speed is 15 meters per second. And because our ground is our reference point and gravity is negative going down, that means up must be positive. That means that my initial velocity must be positive 15 in the j direction, which implies that C1 is 15j. Okay, because again, when we substitute t equals 0 in here, that all goes away. So therefore, finally, my position, my velocity vector is equal to negative 9.8 t plus 15, all of that in the j direction. Next to that, over here, I'm going to do the position vector in part B. So r of t, not r dot t, r of t is going to equal the velocity integrated. So it's going to be negative 4.9 t squared plus 15t, all in the j direction, because it's just vertical motion, plus constant of integration number 2. But in this case, because the initial position was ground level, which we've taken to be 0, the initial position is 0, which implies that C2 is equal to 0 also, because again, these t's become zeros and the whole thing becomes 0. Nice one. That means that the position vector we want is the same as above, but without the C2. So I'm just going to rub that out after duplicating it because maximize laziness. Nice. Let's move on to part C. Okay, so when we're looking at the maximum height of the ball, we first want to consider what type of function are we even looking at. Now we know it's straight line motion, but how is the particle behaving in that straight line motion? So if we look at the position vector, we can see that it's a quadratic, and importantly, it's a negative quadratic. So we know that the shape of the motion of the particle is going to be quadratic, meaning we will get a maximum value. In context, this just means that the cricket ball is going to go up in the air until a certain point and it's going to stop at that height and then start coming back down to earth. That's represented two-dimensionally here, but of course it's one-dimensional because it's just straight line motion. Now that's a stationary point, and if you're not really that good at finding stationary points or even understanding their nature, make sure you click the card that's on screen now or click the link in the description. I talk about why we used first and second derivatives to determine things like stationary points in that video. I think you get a lot out of it. Make sure you watch that, then come back and continue watching this guy. Okay, so I know that I need to find the first derivative and let it equal 0 if I want to determine a maximum height. So when I find the first derivative, I already know it. It's actually over on the right-hand side of my page. There we go. And I'm going to let that equal 0. So negative 9.8t plus 15 equals 0. Solve for t. I get 9.8t equals 15. T equals 15 over 9.8. seconds. Now you can approximate that and figure out what it actually is, but it's just not necessary in this case. I'm just going to leave it as a fraction. So keep in mind that's when the particle is at its maximum height. Now I just need to find where by subbing it back into the position particle formula. So we get r of 15 over 9.8 equals minus 4.9 15 over 9.8 all squared plus 15 lots of 15 over 9.8 in the j direction, of course. And when we use our calculator, we get 34.44 meters. Notice that the initial velocity, by the way, was meters per second. So this is time in seconds. This is height in meters. That's 2 decimal places. So I might even indicate that with 2dp. And finally, in part D, we have when does the ball return to ground level? Now, that's just going to be when the position of the particle, which is expressed by r of t, which equals negative 4.9 t squared, plus 15t in the j direction, when that thing equals 0. So I get negative 4.9 t squared plus 15t equals 0. I can factorize out a t, and I get negative 4.9 t plus 15 equals 0. So this is going to give me two solutions here. The first solution being t equals 0. That's trivial. We already knew that from the initial position of the particle being at ground level. The second one's the interesting one. So I'm going to solve that one in green. It's the negative 4.9 t plus 15 equals 0. So negative 4.9 t plus 15 equals 0. So 4.9 t equals 15. T, whoops, off the screen now, I'll go off to the side here. T equals 15 over 4.9 seconds. Now, if you wanted to approximate, you can, for 3.06 seconds in 2dp. So that's when the ball returns to ground level. And finally, we've arrived at projectile motion. Now, just quickly, so we're all on the same page, projectile motion is two-dimensional for our instances here in specialist mathematics. So we're going to be looking at this I and j Cartesian plane, I suppose. It's not really the Cartesian plane, but it's an I and j plane of sorts. I've drawn a rough example of the path of a projectile. Now, because the only force acting upon it in mathematics that we're looking at is gravity, it's always going to be quadratic in nature. So the first thing that we need to know or need to figure out is what the initial velocity of the particle is. So I've represented the initial velocity with a green arrow here. Typically, we denote that initial velocity vector as u. And we also need to know what angle of theta is that particle being launched at. Now this does two things, and I'm going to draw them at a different scale down below. Okay, so I've done a little diagram here to show that we can separate the initial velocity vector into two components. The I component, which is the horizontal, which I've labeled x, and the vertical component j, which I've labeled y. Now I can write what those two components are by considering the magnitude of the initial velocity vector and also the angle, right? So x is going to be equal to the magnitude, so the speed of the initial velocity, multiplied by cosine of the angle between the ground and the vector. So u cos theta, magnitude of u cos theta. The y component here can be represented by something very similar. It's the magnitude of u times sine of theta. So therefore, underneath this, I'm just going to write the initial velocity, so r dot 0 of any vector in projectile two-dimensional motion is going to be u, the magnitude of u multiplied by cos of theta in the I direction, plus the magnitude of u multiplied by sine, not cos, sine theta in the j direction. Okay, now that we've established all that, let's move on to our first question and use this information. Okay, projectile motion question number 1. We've been given the position of a projectile at time t, 400t in the I direction, 500t minus 5t squared in the ej direction for time must be greater than or equal to 0, naturally. Alrighty, now that we've read the question, I'm going to make it a bit smaller so I've got a bit more space to work here. And part A wants us to determine when it reaches the ground again. Presumably it's fired from the ground. So we just need to determine when the j component equals 0. Forget the I component, it's just the height. When that equals 0, we're good. So therefore the j component, 500t minus 5t squared equals 0, and we solve that. I'm just going to first of all divide everything by 5 just to simplify it, and then factorize t. Which gives me two answers, t equals 0 or t equals 100. And my answer therefore is when t equals 100. 100 seconds, that is, I think. Doesn't tell me the units of time. I'm going to assume it's in seconds. Okay, part B asks us, what is the speed when the particle hits the ground? Now for speed, it's the magnitude of a velocity, so I need to determine what the velocity vector is. So r dot t is going to be equal to 400 in the I direction plus 500 minus 10t in the j direction. Okay, so I need the magnitude of the velocity vector here. So I'm going to say, therefore, speed equals the square root of 400 squared plus 500 minus 10 lots of t all squared. But I can determine what the time is when it hits the ground again. I know it's at 100. So I'm going to put that information in here. Square root of 400 squared plus 500 minus 10 lots of 100 all squared. 10 lots of 100 is 1,000. 500, it doesn't matter. I was about to explain it all and go through it all manually, but at the end of the day, once you have a square root and a bunch of values, you can go ahead and just pop it in your calculator in a tech active exam, which is exactly what I'm going to do right now and get an answer. Alrighty, went ahead and popped it in my calculator and I got 640.31 meters per second of speed. That's pretty darn fast if you ask me. Okay, let's move on to part C. It wants the maximum height of the particle, so let's determine when the first velocity vector equals 0. So it's 400i plus 500 minus 10t in the j direction, and that's got to equal 0. Now, it says maximum height, so it must be when the height is equal to 0. So I'm going to say, therefore, 500 minus 10t must be equal to 0. Divide everything by 10. 50 minus t equals 0. T must equal 50 seconds, which should make a lot of sense to us. And we can verify that answer because we know that it's fired from the ground. We know it hit the ground again at 100. And because it's parabolic in nature, it should be symmetrical, and halfway between 0 and 100 is 50. So the maximum height should be when t equals 50. Now, unfortunately, it didn't just want the time when the height was maximized, it actually wants what the maximum height is. So we're going to substitute that into the j component of the original position vector. Okay, so r of 50, when we're subbing 50 in, it's going to be 500, oops, excuse me, it's not 500, it is, if I'm looking correctly, it is 500, it's 500 lots of 50 minus 5 lots of 50 squared. Again, pop that in our calculator, and our answer is 12,500. 12,500, presumably meters up in the air. So that's pretty high up in the air, 12.5 kilometers. Interesting. And finally, part D, it wants us to find the initial speed of the particle. We can do that by finding what is the velocity vector when t equals 0. So we've got r dot of naught is equal to 400 in the I direction plus 500 minus 10 lots of naught in the j direction, which is going to be 400i plus 500j. And initial speed, so that's the initial velocity vector. The initial speed, therefore, is equal to the square root of 400 squared plus 500 squared. 400 squared plus 500 squared and square rooted is going to be approximately 640.31 meters per second, which actually matches exactly our speed when it hits the ground, which should make a lot of sense because, again, these 2 points in time should be symmetrical to one another, and hence the gradients of them, the speed, should be exactly the same. Obviously, different velocities, one will be down, one will be up, but the speed of them will be the exact same. Alrighty, we've got 2 more questions here. Thank you for sticking around. If you've been enjoying the video so far, make sure you click the like button. And if you've got any questions or comments, make sure you put them in the comments below as well. We've got 2 more questions. Let's keep going. So here we got a particle is projected from a certain angle with the plane or the x-axis, and it's projected at a velocity of 30 meters per second. So let's put that information down. Okay, with all that information down, we need the initial velocity vector. If you recall from the projectile motion, the initial velocity is going to be u cos theta in the I direction plus u sine theta in the j direction. So substituting what we know in, we get 50 cos of 30 degrees, that is, and 50 sine of 30 degrees. Now this looks like a tech-free question because 30 degrees is one of our known angles, so we can simplify now to 50 times root 3 on 2 plus 50 times a half, which again simplifies down to 25 root 3 in the I direction, I missed those above, I and j, and plus 25j. So my initial velocity vector is 25 root 3i plus 25j. Now that's the initial velocity. The second part is asking us for the velocity vector in terms of time. So for that, we need to start with acceleration and work up to time in velocity. So we're going to say r double dot t is going to be equal to negative 9.8 meters per second squared. In the, I don't really need the meters per second squared, it is the units, but it's just in the j direction here. And therefore r of time is going to be equal to negative 9.8 t in the j direction plus c1. Now we know what c1 is. We know what the initial velocity is. It's going to be equal to that velocity vector before. And so I'm going to be looking at my j component of negative 9.8 t is going to combine with my little negative 25 over here in the j direction. So therefore, the r dot t is going to be in the I direction, 25 root 3 I plus negative 9.8 t plus 25 in the j direction. Nice one. Thirdly, it wants the position vector, so rinse and repeat. I've just got to double check where it's launched from. It's point horizontal ground, speed of this, angle of this, blah, 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 blah. So it doesn't actually tell us that it starts from the origin, but we can probably go ahead and assume it starts from the origin. So I'm going to say C here is the position vector, so R of t. It's going to equal to the derivative, or the integral rather, of the velocity function, which is going to be 25 root 3 t in the I direction, plus negative 4.9 t squared, plus 25t in the j direction. Now we have the constant of integration number 2, but I'm going to go ahead and assume again that it's projected from the origin, and just based on having not more information than that, say that C2 must be 0. But I have considered it, I'm just considering it to be 0. And finally, D says the Cartesian equation of the path. So this is just where we're going to take the time variable and represent it in terms of x, sub it into the y variable. Okay, so I'm going to be treating this, the I direction, as x, and I'm going to be treating this as the y value, or the j direction, right? Because we can represent any vector r of t in terms of x in the I direction plus y in the j direction, and we can get the Cartesian equation from that. Alrighty, so x is going to be equal to 25 root 3t. Therefore, t is going to be equal to x on 25 root 3. But I probably want to rationalize the denominator. So timesing top and bottom by root 3, I'm going to get root 3x over 25 times 3 after I've rationalized, which is going to be 75. Okay, now that's an expression for x. I have a coefficient of x, it's root 3 on 75, and I'm going to substitute that. So I'm going to write sub t into y and get an expression for y equals something. So y, which equals negative 4.9 t squared plus 25t, is going to equal negative 4.9 of t squared, but t is this guy now, which I'm going to duplicate and pop in. That's squared plus 25 lots of, and I'm going to run out of room, but we'll see how we go. Duplicate again, maybe make a bit smaller so it fits. There we go, beautiful. And now I can simplify and solve if possible. Okay, let's see how good my maths is. So negative 4.9 out the front. In the brackets, root 3 squared is 3. So we're going to get 3x squared on the numerator. 75 squared, going to need the calculator for that one. 5625, 5625. I'm just going to check if that's divisible by 3. It is 1875. So I'm going to simplify this now into x squared on 1875. Nice one. And plus now 25 and 75 are easily divisible by one another. So that's 1 over 3. So that's going to be plus root 3x on 3. And that's going to be the Cartesian equation. Y equals negative 4.9x squared over 1875 plus root 3x on 3. Pretty ugly, but it is what it is. Alrighty, and finally, we're looking at a problem-solving type question using projectile motion. So a ball is thrown from ground level, so we know the initial position. Initial speed, we know that's 50, so I'm going to write u equals 50 just to get that out of the way. I know there's a wall of height 20 meters at a distance of 100 meters from the origin, and it wants me to find the smallest possible angle of projection for the ball to pass over the wall. So actually, theta is what we're searching for in this question. So I'm going to draw a quick diagram. So I've got a projectile here, and at some point, let me just draw a horizontal line here. At some point, there is a wall that is 20 meters high, and that's 100 meters away. So I'm going to guess that this coordinate is 100, 20 for x and y. At some point in time. T, I don't know what time that is. Okay, let's just start with well, if I've got a position, I suppose, in time, I should probably get my position vector. So I'm gonna make this diagram a little bit smaller. Now I've, I guess, comprehended it. Pop it over here to the side, and let's just start with the fact that if it's projectile motion, r double dot of t must be negative 9.8 j. And therefore r dot t is equal to negative 9.8 t j plus c1. I know my initial velocity is 50. I don't know the angle, so I'm going to have to leave it as theta for now, but we can still sub it in. And we get r dot t is equal to u, which is 50 cos theta in the I direction, plus negative 9.8 t plus 50 sine theta in the j direction. Right, that's initial velocity. Let's go one step further and get initial position by saying r of t is equal to 50 cos theta of t in the I direction plus negative 4.9 t squared plus 50 sine theta t in the j direction. You can go ahead and show that the second constant of integration here, c2, is going to equal 0, but it tells us it projects it from the origin, so I'm going to assume that c2 is equal to 0. I might even just write in brackets c2 equals 0. Okay, just to show my working, show that I understand that. Right, so we have a position, and I know what the x and the y values are at a certain point in time. I don't know when the time is, but I know the x change, or 50 cos theta of t, must be equal to this 100 meter change. At the exact same point in time, this expression here for t must be at height 20 meters. So I'm going to go ahead and I guess make all this work that I've just found much smaller. Again, pop it over to the side here and just work with, oops, let's just pop it here. And just work with these x and y. So I'm going to say 50 cos theta t, 50 cos theta t, at some point in time, I don't know what it is, must be equal to 100 meters. okay? And I'm gonna solve for t, similar to what we did above, right? So I'm gonna get t is equal to 100 over 50 cos theta, which is gonna simplify nicely into t equals 2 over cos theta. Now, I know what the time is if I knew what the angle was, but with the beauty of graphics calculators, I can now sub this into the other equation, pop it in a graphics calculator, and output an answer without ever actually knowing what t is. The reason I can do that is because t in both x and y are the exact same value, so I can kind of bypass the fact that I don't know what t is because I know that t in this expression here is the exact same. Right, so this expression here, instead of t's, I'm going to put in my expression for t. So I get negative 4.9 multiplied by 2 over cos theta squared plus 50 sine theta times 2 over cos theta. And all of that must be equal to the height at the time when the x is 100, which is 20. Right? Because if I want this particle to just clear the wall, I want it to just be 200. Now, it can't be exactly that height, but it can be at the smallest, this height. Okay, as usual, I've popped some of the information to the side. We're just looking at this, and I'm just going to say using graphics calculator, and I'm going to show you that on my screen now. Okay, here I am in the TI Inspire student software. I'm going to show you two different ways you can solve this question. The first is using numerical solve. So you go to algebra, so menu algebra, and then numerical solve, and you just put in what you want to solve and which variable for. First, double check that you're in degrees mode because we want the angle in degrees. So now I'm going to pop this in here. I'm going to have negative 4.9 lots of fraction, control divide, 2 over cos of, I'm just going to call it x for my angle for now, all that squared, plus 50 sine of x times by another fraction, oops, wrong button, escape out of that, 2 over cos of x, close bracket, equals 20. And all of that I'm solving, comma, for x. Close my end solve and hit enter. And I get 23.39, which is more or less 23.4 degrees of angle. Now, the other way you can solve it is instead of getting this entire expression in terms of just my angle, I can take my x value and my y value and solve them simultaneously, parametrically, I suppose. So to that, we'd go menu, algebra, and solve system of equations, and not linear, but we solve system of equations. We have two variables, x and y. You can call them x and t. I might even do that. Call this one t. So it's very clear which variable is which. So now, my first one was 50 cos theta t. So it's going to be 50 cos of x times time. All of that was equal to my 100 meters. And my y1 was negative 4.9, oops, that's a 2, 4.9 t squared. And then we had plus 50 sine of x times t. And all of that was equal to 20 meters high. Alrighty, I can just go ahead and press enter here, but I want to add a couple of conditions because I don't want time to be less than 0, and I also don't want the angle to be obtuse. I want it to be an acute angle. So I'm going to first of all go control equals to get this vertical line, which represents my given symbol. So this is telling the function that I want it to impose restrictions on it. The first restriction is that time is greater than 0. So that should be a pretty easy one. Spacebar, and 0 is less than x, which is less than 90. Okay, so my angle has to be between 0 and 90 degrees. And hit enter, and we get a few things here. First of all, t equals 2.179 seconds. At that point, the angle is 23.39 degrees, which you can see matches up above our other angle here, 23.39 degrees. But as you can see, there are multiple times and different launch angles. So at 9.55 seconds, if the launch angle is 77.9 degrees. So given the angle of launch, it will clear that wall, but at different heights. So using the graphics calculator to find the smallest possible angle that the ball goes over the wall, theta must be equal to 23.4 degrees. Okay, so that's an example of a harder problem where you've got to solve for initial velocity or solve for initial launch angle, but the process remains the same. Start with acceleration, use your initial velocity or initial angle, whatever you've got, get a position vector, and then use your graphics calculator to solve. Alright guys, thank you so much for watching. If you enjoyed the video, make sure you click the like button and like it. If you've got any questions or comments, make sure you leave them down below. On the screen here is a YouTube recommendation for you to click, and make sure you subscribe to the channel for more maths content. See you next time.